After getting the concept of phase space, phase point, phase trajectory and density distribution function in phase space, now we are at a stage to deal with a very important theorem of classical physics, and that is actually the Liouville theorem. So in this lecture we are going to know about the Liouville theorem, what this theorem actually states and how we can prove this theorem. And after that we will also see that what is the physical significance of this Liouville theorem. So first of all we are going to know about this Liouville theorem, what this theorem actually states. First of all we have to know. As you know, we have studied in the previous lecture that the dynamical state of a system at any given time is represented by a particular phase point in the phase space, and that phase point is actually specified as qk/pk, where you know that these qk's are actually the position coordinates and pk are the momentum coordinates. Okay, and as the system is of dynamical nature or kinetic nature, so you can say that the phase points actually move in the phase space. And you have studied in the previous lecture that whenever there is a motion of the phase point, that motion takes place along a particular trajectory which is called phase trajectory. Okay, and if your aim is to determine that phase trajectory, you have learnt in the previous lecture that we can find the phase trajectory by solving the Hamilton's canonical equations of motion. Okay, so solving the Hamilton's canonical equations of motion, we are able to determine the phase trajectory of a phase point which it describes in the phase space. So what are the Hamilton's canonical equations of motions? We have studied these things in the earlier lecture and also in very detail in my playlist of classical mechanics. You have definitely studied these things. You know that the Hamilton's canonical equations of motion are given like this: qk dot equal to del h by del pk, and pk dot is equal to minus del h by del qk. Here you know that this function h, which is actually a function of qk and pk at a given time, this is called Hamiltonian of the system. Here this subscript k stands for 1, 2, 3 and so on up to f, where f is the degree of freedom of our system. So these are the Hamilton's canonical equations of motion, which are actually the first order partial differential equation. And as I have told you that these equations are used to find the phase trajectory of the particle described in a phase space. Okay. Now, since the phase points are in motion, so definitely in phase space, these phase point moves from one region of the space to another region. And so the number of phase points may decrease in a particular region and it may increase in another particular region. And that's why we say that the phase point density changes with time. Or you know that the density of phase point is also called distribution function or probability distribution function. So in general you can say that the probability distribution function changes with time in case of a dynamical system. Actually the aim of this Liouville theorem is to determine how by which rate this density distribution function changes with time. So the prime aim of the Liouville theorem is to find the rate of change of the density distribution function. Okay. In fact, this Liouville theorem has two parts. we will understand what are these two parts of the theorem first of all, and then one by one we will prove these two parts of the theorem. Actually, the first part of Liouville's theorem is called the principle of conservation of density in phase space. Okay. In fact, according to this principle of conservation of density in phase space, uh, the rate of change of density of phase point in phase space is equal to 0. This is the statement of this first part of the Liouville's theorem. When you say that the rate of change of density of phase point in phase space is 0, mathematically you say that this d rho by dt equal to 0. It means what? It means this rho as a whole remains constant. It means if you consider that this boundary represents the boundary of a phase space, then in a particular region, let us say this, the phase point density may decrease, but in another region of it, equal number of phase point will increase. So as a whole, the total density of the phase point do not change with time, and that's why we simply say that the rate of change of density of phase points or rate of change of distribution function is simply equal to 0. So this is the first part of the Liouville's theorem, which is called principle of conservation of density in phase space. Okay. Now, the second part of this theorem is known as the principle of conservation of extension in space. In fact, according to this part of the theorem, the volume at the disposal of a particular number of phase points remains conserved throughout the phase space. It means if you consider that this delta gamma is the hypervolume of the phase points in the phase space, then this hypervolume does not change with time. It means you can see that if this is the boundary of a phase space, and in a particular region this boundary gets distorted like this, then definitely in another region it will also distorted, and the amount of the volume which will decrease in one part of the region of a space, equal amount will increase in another part. So as a whole, the shape of the boundary may change, but the total hypervolume of phase point in this phase space will never change with time. And that's why mathematically you can say that the rate of change of this hypervolume is equal to 0. So mathematically we write d dt delta gamma is equal to 0. So these are the two parts of Liouville's theorem. I hope you have understand what are these two parts of Liouville's theorem. Now one by one we will try to prove this theorem. Okay. So the proof of the first part of theorem is somewhat lengthy, but the proof of second part is very small, very short, and you can understand these two proofs very easily. So let us first of all see the proof of the first part of this theorem. And for this we consider that this S, you can see this figure, S we have assumed it is a closed surface. Okay, and this closed surface S bounds a volume V inside it, or in other words you can say that V is the volume bounded by a closed surface S. When you say volume V, this means this is geometrical volume. Don't confuse this volume V with the volume in phase space. Actually, volume in phase space is called hypervolume, which is actually the product of the volume of geometrical space, that is the position space and the momentum space. But this volume V represents only the volume of position space. Okay, so V is the volume of position space, or you can say in other words that V is the geometrical volume enclosed by the closed surface S. Okay. Now let us consider a point P on this bonding surface S, and we also consider a very small elementary surface surrounding this point P, and that elementary surface has an area, let us say ds. As you know that the elementary surface is always a plane surface, and a plane surface is treated like a vector. So the vector area of this elementary surface is equal to this vector ds, and it is normal to that elementary surface. Okay. And if you assume that n hat is the unit normal vector, that is n hat is a unit vector normal to this elementary surface, then this area vector ds may be written like n hat times ds. Okay. Now we consider that the phase points are moving out through this elementary surface, and the velocity with which the phase points are moving out from this elementary surface, we consider this is equal to vector v. So vector v represents the velocity with which phase points are moving out from this elementary surface. Okay. Now we consider an elementary volume, let us say dv, inside this volume v, and we consider that this rho is the density of phase point at this particular point. Okay. So if your aim is to find how many phase points are moving out through this elementary surface per second, or the rate of flow of the phase point through this elementary surface, if your aim is to find out that, how you can find it. So for this, let us consider just a cylinder, and this cylinder has a cross-sectional area, let us say equal to ds. Okay. And the phase point which enters this surface ds at time t equal to 0, that leaves the another end of this cylinder at a time t equal to 1 second. So you can say that the phase points describes this cylinder in 1 second. So the number of phase points crossing through area ds in 1 second will be equal to what? That will be simply equal to number of phase points contained in this cylinder, which has a cross-sectional area of ds and length equal to the distance described by the phase point in 1 second. As you know that the velocity of phase point is v, so the distance described by this phase point in 1 second will be simply equal to v. Okay, this will be equal to v, because you know that distance, if distance is L, then this distance will be speed into time, that will be equal to v. So distance described by any particle in 1 second is simply equal to the speed of the particle. Okay. In this figure I have shown that this velocity vector is actually in the direction of the area vector, or on the line of the area vector, but in accordance with our supposition, this velocity vector makes an angle theta, as you can see this figure. So in this condition, actually we will have to take the component of this velocity along the area vector, and that component will be not equal to v, but that will be equal to v cos theta. V cos theta. So this length you can take will be equal to v cos theta. This is v cos theta. Okay. Or if you take the component of this area vector along the velocity, that will be ds cos theta. So you can say that this length of this cylinder described by the phase point in 1 second in the direction of the area vector is v cos theta. Okay. So what will be the volume of this cylinder? This volume will be area of cross section multiplied by length of the cylinder, which is V cos theta. Okay, but this theta is the angle between the vector ds and v. So from the definition of a scalar product of two vectors, you can say that this will be equal to v dot ds. This is actually the volume of this cylinder. Now, as the density of phase point is rho, and density means number of phase point per unit volume. So if rho is the number of phase point per unit volume, then what will be the number of phase point contained in this cylinder? As the volume of this cylinder is V dot ds, so this number will be simply rho times V dot ds. I hope you have understand. This actually represents the number of phase points passing through this elementary surface in outward direction. Okay, so now you can directly say that the number of phase points moving out through this elementary surface ds in 1 second will be equal to rho v dot ds. Okay, I think you have understand this fact. So see, I have mentioned it here that the number of phase points flowing out per second through a surface element of ds, area ds. If you denote that number by the symbol dn by dt, then that will be equal to rho v dot ds, or in other words you can say that this is rho v dot n hat ds, because this area vector ds is equal to n hat times ds. Okay, and as I have told you that this velocity, this v is actually the velocity of phase points in this region of the surface element. Okay, so this is the number of phase point passing through this elementary surface ds in 1 second in outward direction. Now if your aim is to find the total number of phase points moving out through the whole closed surface, how you can find it? It is very easy to say that if we know the number of phase points passing through an elementary surface ds per second in outward direction, then if you will integrate this result for the complete closed surface, then you will get the total number of phase points moving out through the entire closed surface S. So you can say that the total number of phase points flowing out per second through the entire surface S, that will be what? That is delta n by dt, and that will be equal to surface integral of this much. That is the surface integral of rho v dot ds. Here double integral means the surface integral, you know that surface integral is evaluated by double integral. So we have used the two sign of integration, and this sign of integration has been encircled, which actually represents that our surface under consideration is a closed surface, and that's why we have encircled this sign of integration. But you can also write this expression by writing the single sign of integration. It is not necessary to write down these two sign of integration, but it is more convenient. So I have used the double integration here to represent the normal surface integral. So the normal surface integral of this vector field rho v it just represents the total number of phase points moving out through the whole bounding surface or whole closed surface S. Okay, but as you know that if the number of phase points is moving out through the surface, definitely the number of phase points inside the surface will decrease, and as the phase point is neither created nor destroyed, so definitely the number of phase points decreased per second inside the surface, must be equal to the number of phase points moving out from the surface in outward direction. Okay. So to get the value of number of phase points that decreases in 1 second inside this surface, let us consider this elementary volume inside this volume V. You can see, if we consider that this elementary volume is dV and rho is the phase density, so at any time t, the number of phase points contained in this elementary volume will be what? Since rho is the number of phase point in unit volume, so number of phase point in volume dV, this will be simply rho into dV. Okay. And if you want to find the total number of phase point inside this bonding surface, then that will be simply equal to the integral of rho dV with respect to volume V. Okay. Now, if you want to find the rate of decrease of number of phase point inside this surface, what you will do? We will simply differentiate this number with respect to t with negative sign. Negative sign only represents that this number is decreasing, and so we will write the number of phase point decreasing per second inside the surface will be equal to what? That will be minus d dt integral over v rho dv. Okay. This is the number of phase point that decreases in 1 second inside the surface. So you can see I have mentioned it here that the rate of decrease of number of phase point in volume V, that is equal to what? This is minus d dt integral over v rho dv. Okay. And if you want to operate this differential operator d dt on rho, you have to write minus integral over v del rho by del t dv. One thing here is very remarkable and you have to understand this. I have written this rate by the operator d dt, but when this operator is operated on the function rho, then we have written the partial derivative, not the ordinary derivative. Can you say why this ordinary derivative is now written like partial derivative? Because you know that this density distribution function rho is not only a function of t, but it is a function of 2f plus 1 independent variables. And these 2f plus 1 independent variables are what? There are this rho depends on qk and qk has f values. Rho also depends on pk and pk has also f values. And apart from these two, this rho is a function of t. Here we are differentiating this rho with respect to t, but since rho is not only a function of t, so if your aim is to find the time derivative of rho, you have to keep the other variables constant, and that's why we take the partial derivative instead of the ordinary derivative. Okay, so I think you have definitely understand why this operator d dt has been changed to del t when it is operated on this function rho. Okay, so this is the rate of decrease of number of phase point inside the volume V, and you have obtained that the rate of flow of phase point out in outward direction, that is equal to rho v dot ds integral over s. But as you know that these phase points cannot be created, it cannot be destroyed. So the total number of phase point must be constant. It means the number of phase point which decreases inside the surface, exactly that number of phase point will flow out through the surface. And so we can equate these two values. You have calculated that this integral over s rho v dot ds represents the total number of phase points moving out through the surface, and this minus integral over v del rho by del t dv, this represents the number of phase points decreased per second inside the surface S. So these two will be equal because the phase points are neither created nor destroyed. So these two numbers will be definitely equal. Okay, and so I have equated these two values, that is integral over S rho v dot ds is equal to minus integral over v del rho by del t dv. Okay, now you can see in this equation 4 the RHS is a volume integral. This is a definite integral with respect to volume v, and this has been integrated for the entire volume v. Okay, so RHS is a volume integral, but see the LHS of this equation. LHS is a normal surface integral. But you have studied Gauss's divergence theorem in your course on elementary vector calculus, and you know that Gauss's divergence theorem actually gives a mathematical tool to transform or to convert this normal surface integral into the volume integral. Okay, so applying the Gauss's divergence theorem, you can change this surface integral which is in LHS of equation 4 to its equivalent volume integral. So according to Gauss's divergence theorem, what will be this normal surface integral equal to? This will be, according to this theorem, this will be equal to the volume integral over V of the divergence of the vector field rho v. So applying Gauss's divergence theorem, you may write that the integral over S rho v dot ds is equal to integral over v divergence of rho v dv. Okay, so in this equation number 4, see here, now the surface integral in LHS can be replaced by its equivalent volume integral, and after that what will be our result? You can see it here. So we now get volume integral of divergence of rho v over the volume v is equal to minus integral over v del rho del t dv. Okay, now if you take this term in RHS of this equation in LHS, you can write this expression like this. This is integral over v divergence of rho v plus del rho by del t dv equal to 0. Now you can see in our discussion we have assumed an arbitrary closed surface S. This is just arbitrary. I have never said that this surface is spherical or cubical or a particular shape. This is just arbitrary. You can take any shape and size of this surface. Okay, only restriction is that this surface is a closed surface and it encloses a volume v. Since the bonding surface S which bonds the volume v is arbitrary, so you can say that this volume v for which we are going to evaluate this integral is completely arbitrary. So the result obtained in this equation 5, that is the value of the integral which is equal to 0, is not due to the particular any value of volume. Okay, so the shape or the volume is not responsible for this 0 result. Okay, so you can say that this definite integral is 0 and this volume is not responsible for this 0 value of integral. So what does it mean? It means as the integral is definite, so definitely this integrand must be equal to 0. Okay, integrand must be equal to 0, and so on this basis you can say that divergence of rho v plus del rho by del t is equal to 0. See this equation seriously, and you can see this is just a well-known equation. You have studied this form of equation several times during the study of your physics. Okay, actually this is the well-known equation of continuity. While studying the quantum mechanics, you have studied the equation of continuity. When you have studied the classical electrodynamics, then you have studied the equation of continuity. Okay, you have studied these things in several times. Okay, in hydrodynamics you study the equation of continuity. Just like that, this form of equation implies that this is just an equation of continuity. And you know, any equation of continuity is actually a mathematical equation of a conservation principle. So definitely this equation of continuity represents a conservation principle. Actually, this equation of continuity is for the distribution function rho. So actually, this represents the conservation principle of the density distribution function. So the result uh, obtained in this equation A1 actually refers that the density distribution function in phase space will definitely remain conserved. But uh, the mathematical form which we have written for the first part of the theorem was d rho by dt equal to 0. But this equation is not in this form. So now we will try to transform this equation of continuity in this form, that is d rho by dt equal to 0. It means now we have to show that divergence of rho v plus del rho by del t will be equal to d rho by dt. Now we will see. Actually, till now in our discussion, we have not assumed a phase space, but we have only, in our calculation, we have only assumed a geometrical volume, only a position space. But now we extend our result to the phase space, as you have considered that the degree of freedom of our system is f. So you know that the phase space will be equal to of 2f dimension. Phase space will be of 2f dimension. Okay, and in a 2f dimensional phase space, this velocity is vk. Actually, I have written vk here, k runs from 1 to f. Actually, you know, in phase space there are two independent coordinates, one is qk and another is vk, and the time derivative of qk, that is qk dot and pk dot, these actually represent the velocities. These represent the velocities. Okay, so taking the time derivatives of qk dot and pk dot as velocities in phase space of 2f dimension, what will be this term? Divergence of rho v. You know, this divergence of rho v is equivalently written as del dot rho v. And you know, when you define del dot f, let us say del dot f, definitely you have an idea of divergence of a vector function. This is simply equal to del fx by del x plus del fy by del y plus del fz by del z. Okay, or you also write like this. This is del f1 fi by del xi, where I runs from 1 to 3. Okay, here I have not written x1, x2, x3, but I have written x, y, z. But instead of x, y, z, you can write x1, x2, x3, and instead of fx you can write f1, instead of fy you can write f2, instead of fz you can write f3. So in the light of this definition of divergence of a vector field, you can write that this del dot rho v, when we will write the expression for this divergence of rho v in the 2f dimensional phase space, we can write this will be equal to summation over k from 1 to f del qk. Here qk is the first coordinate, rho qk dot, rho qk dot. Actually, instead of the first component of velocity, we write qk dot, and plus del pk operated on rho pk dot. Okay, this is just from the definition of divergence of a vector field. Now you can see inside this square bracket we are going to differentiate rho times qk dot and rho times pk dot with respect to qk and pk respectively. So follow the rules of differentiation of product of two functions, and you can see this will be simply equal to summation over k rho del qk dot by del qk plus qk dot del rho by del qk. These two terms have been written for the first term inside this square bracket, and for the second term you can write rho times del pk dot by del pk plus pk dot del rho by del pk. Okay. Now let us arrange these terms here. So this can be written as summation over k qk dot del rho by del qk plus pk dot del rho by del pk, and plus now this term and this term contains rho, and rho is independent of summation, so I have written here rho outside of this sign of summation, and the remaining factor will be summation over k del qk dot by del qk plus del pk by del pk. Now what are these qk dot and pk dot? What will be how this del qk dot and del qk are related to del pk dot by del pk? All these things we can draw, we can find by using the Hamilton's canonical equation. So you can write the Hamilton canonical equation, and then you will get the idea that for which quantity this qk dot and pk dot stand for, and how these two quantities del qk dot by del qk and del pk dot by del pk are related. So first of all, write the Hamilton's canonical equations. You know these equations I have already mentioned earlier, but I am repeating the same thing here. You know this Hamilton's canonical equations are qk dot equal to del h by del pk and pk dot is equal to minus del h by del qk. Okay. So in the first term in RHS of this equation 6, this qk dot will be replaced by this del h by del pk. Okay, and this pk dot can be replaced by minus del h by del qk. Okay, we will replace. Now we want to know how these two terms are related, that is del qk dot by del qk and del pk dot by del pk are how related. You will see that these two terms are equal in value and opposite in sign, but how you can easily see. So see here, this del qk dot by del qk, you can write del qk, and instead of qk dot from Hamilton's equation you can write del h by del pk. Now you know that the exchange of the operator del pk and del qk is permitted. In fact, according to this term, first of all we have to differentiate this Hamiltonian with respect to pk, and after that we have to differentiate it with respect to qk. But if you differentiate the Hamiltonian first of all by with respect to qk and then with respect to pk, the result will be same. Okay, so the exchange of these two operators are permitted, and therefore we can write this expression del qk del h by del pk equal to del pk del h by del qk. But from Hamilton's canonical equation, can you say that what is this del h by del qk? You know this del H by del Qk is actually equal to minus Pk dot. So instead of this del H by del Qk, we now write minus Pk dot. And so this result is minus del Pk dot by del Pk. So what you are getting here? You can see we have obtained that del Qk dot by del Qk is equal to minus del Pk by del Pk. And as you can see, the second term, since del Qk dot by del Qk is equal to minus del Pk dot by del Pk, so these two terms will cancel out. And that's why we can say that the second term in RHS of that equation vanishes. Okay. So taking the second term 0 and replacing Qk dot and Pk dot from Hamilton's equation, now that equation will become what? This is divergence of rho v equal to summation over k1 to f del H by del Pk del rho by del Qk minus del H by del Qk del rho by del Pk. Okay. You have definitely studied the Poisson bracket in your course on classical mechanics. If you have not an idea or knowledge of Poisson bracket, I will suggest you to go through my playlist on classical mechanics in my channel, and you will find a detailed concept of Poisson bracket there. Okay. So definitely you have watched, and so I hope you have an idea of Poisson bracket. This is just definition of Poisson bracket. Here the two dynamical variables are h and rho, and so from the definition of Poisson bracket we can say that the RHS of this equation is nothing. This is simply equal to Poisson bracket of Hamiltonian H and rho, that is density distribution function rho. So finally we get that divergence of rho v is equal to what? This is Poisson bracket of H and rho, where H is Hamiltonian and rho is the distribution function. Okay. And so the equation of continuity which we have obtained earlier, see here in equation A1, now this equation of continuity can be written in terms of that Poisson bracket which we have obtained. You have seen that divergence of rho v, we have obtained that this is equal to Poisson bracket of Hamiltonian with density distribution function. So instead of divergence of rho v, we will write that term, and the second term del rho by del t will remain at each. So now this equation of continuity can be written like this. This is Poisson bracket of h and rho plus del rho by del t equal to 0. Okay, del rho by del t equal to 0. Now we will see by further calculation that this LHS of this equation will be equal to d rho by dt. But how it is equal to d rho by dt, you can see. As you have learnt earlier in the previous lecture, that the density distribution function rho is in general a function of qk, pk and t. We have learnt or not? Definitely you can remember it. And so if you want to find the value of d rho by dt, you will have to adopt the method of partial differentiation, because rho is not a function of a single variable, but it is a function of 2f plus 1 variables. Okay. So what will be our result? This will be summation over k del rho by del qk times dqk by dt. Okay. Plus del rho by del pk times dpk by dt. Okay, and plus del rho by del t at times dt by dt. Okay, but this dt by dt will be equal to 1, so I have not written, had not written here dt by dt. Okay. Now this d rho by dqk times dqk by dt. You know this dqk by dt can be written like qk dot, and dpk by dt is now written pk dot. Okay, and all other terms are at each. Okay. Now again we will use here the Hamilton's canonical equation. You know from Hamilton's canonical equations that qk dot is equal to del h by del pk. Okay, and this pk dot is equal to minus del h by del qk. So now our equation becomes d rho by dt equal to summation over k del h by del pk times del rho by del qk minus del h by del qk times del rho by del pk and plus del rho by del t. Again from the definition of Poisson bracket you can easily say that the first term in RHS of this equation is nothing. This is simply the Poisson bracket of Hamiltonian H and the density distribution function rho. Okay, so you have shown that this d rho by dt is equal to this much. But earlier you have proved that this sum, that is Poisson bracket of h and rho plus del rho by del t, is equal to 0. You have shown. You can see this equation 8. So now you can easily say that this d rho by dt is equal to 0, and d rho by dt equal to 0, you have seen that this is nothing. This is simply the first part of Liouville's theorem. So you can say that the density distribution function remains conserved in a phase space. Okay, so this is the first part of Liouville's theorem. Although calculation is somewhat lengthy, but it is very interesting, very simple, and if you have an idea of the vector calculus, Gauss's divergence theorem, and some of the idea of partial differentiation, you can easily understand it. You can easily get the things. Okay, so I hope definitely you have learned all these things and definitely you have enjoyed. Okay, now we are going to see what is the proof of the second part of Liouville's theorem and how we can prove it. Okay, actually to prove the second part of Liouville's theorem, let us consider a hypervolume delta gamma in phase space. Okay, you know that this hypervolume is how defined. You have learnt all these things in the previous lecture. This hypervolume delta gamma in phase space is just defined like this. This is integral pi dqk dpk. Actually here this pi, you know, stands for the multiplication. This represents the product of dq1, dq2, so on dqf, dp1, dp2, so on dpf. Okay, so this is the hypervolume in phase space which we have assumed. Okay, now what will be the number of phase points in this hypervolume? As you know, if rho is the density distribution function, that means rho is the number of phase point in unit volume of phase space, unit volume. So in unit volume the number of phase point is rho. So in volume delta gamma, what will be the number of phase point? That will be simply rho into delta gamma. So the number of phase points in this hypervolume delta gamma is given like this, n equal to rho into delta gamma. Again, you can say, as you have learnt earlier, that as the phase points are neither created nor destroyed, so this total number of phase points in the given phase space must be constant, must remain constant, must remain conserved. Okay, and if it remains conserved, then what you can write mathematically? As n remains conserved, so we can easily say that dn by dt will be equal to 0. dn by dt will be equal to 0, you can say. So I have written here that this d dt n equal to 0. But n is equal to rho times delta gamma. Here we actually allow both rho and delta gamma variable. It means the shape of the boundary of the phase space is getting changed. Okay. So you can write this derivative like this. This is d rho by dt delta gamma plus rho d dt delta gamma, and that is equal to 0. But from the first part of the theorem, you have just proved that this d rho by dt is equal to 0. So this first term vanishes, this is equal to 0, and that's why we can say that this second term rho d dt delta gamma is equal to 0. But as you know that this rho is not 0 because this is density of phase point or density distribution function. So definitely we can say that if there is 0 in RHS and rho is not 0, then what will happen? Then definitely d dt delta gamma will be equal to 0. And this is actually the mathematical form of the second part of Liouville's theorem you have learned. Okay. In fact, what this result actually implies, it means this delta gamma does not change. It means hypervolume of the phase space remains constant. Although during the motion of phase point, the shape of the boundary may change. It means the region may be contracted in some region, but when it will contract in some region, in equal amount it will expand in another region, and that's why the total hypervolume will remain constant. Okay. And so this is actually the physical significance of this Liouville theorem. Actually Gibbs has explained the physical significance of this theorem, and according to Gibbs, this principle is known as conservation of extension in phase space. Okay. And so as I have told you that you can say that in accordance with this theorem, any extension in phase space with moving boundary retains a constant volume as time passes. Volume remains constant, although shape may change. I have mentioned it here, you can see. However, its shape may in general change with time, but the total volume of phase space will remain conserved. So this is just like an incompressible fluid. So this is the physical significance of this Liouville theorem. So I hope you have definitely understand clearly what is this Liouville theorem and how we can prove it. Okay. And I hope you have enjoyed the lecture, and if you have enjoyed, then I will be very happy because my labor will be then actually rewarded. And so thank you very much.